Okay, Lorenzo, I think why don't we get started?
Okay. Good afternoon, everybody. I'm Lorenzo Veschini. I'm a research assistant in James Glazer Lab. And today I will show you a quick walkthrough on how we can turn a simulation that we have built as we have seen these days, and we will see the next days, into a Python-only Jupyter notebook. And if we have time, also Python-only script that we can run in different ways. And the take-home message is that we will use the angiogenesis simulation that James has presented yesterday. So we won't spend much time on that since we know that. And Pedro will explain extensively tomorrow how that is built. So my concern today will be like showing a little bit how we can turn this kind of simulation into this kind of data, where we can see what happens when we modulate parameters and we see what happens at matrix. And we will cover this a little bit more extensively on Saturday. And today is just a quick priming on that. So let me see if my slide deck wants to move forward. Yes, it wants. So this is the usual outline. And learning objective for this short session, just looking at angiogenesis simulation once more. TweetIt versus Python application programming interface API. Why and when to use it. A quick recap, just a cheat sheet. I won't go through that very quickly, but it's really essential when you do this. If you want to follow along today, especially on Saturday, having installed the CC3D via the conda method. And if you follow along what is written in the cheat sheet, you will also be able to assess it via Jupyter notebooks on Jupyter Lab. And then I will really walk quickly throughout is assist the angiogenesis simulation with the API, set some steering slider for interactive visualization, and how to run the simulation interactively. And as an extra, if we have time, just preparing this script as an independent Python script for further use. Okay, the angiogenesis simulation we have seen yesterday, and we have learned probably that it can give 3 different results. Take-home message for this is that simulation was developed to kind of map to certain experimental results created with the so-called matrigel assay. And perhaps these are not necessarily the most appropriate pairing, but just a quick overview on what kind of results we can get with the simulation and which are the kind of results we get with the matrigel assay. And we want to, and the simulation was built to map this to that and consider a few things. Chemotaxis which we haven't seen yet. We will see that tomorrow, and Pedro, I think he will also explain that. And we have seen cell contact that is important, and cell secretion that we have just seen. So we are just missing one step in the way we build the simulation, and tomorrow you will have the whole picture about that. We have a reference model that's been published. So this story has been already published and validated and studied. And this reference model, you can pick it from here, and is done by Rormax and Prof. Glazer and other people. Okay. So TweetIt versus Python API. When? That's, I think, the most essential question and the most important part of this short talk. When to use TweetIt player? Almost always, 90% of your time, probably. Because it's when you want to build a simulation piece by piece, you want to look at intermediate outcomes, you need convenience about facility to steer simulation runtime, you want to observe the dynamics of simulation metrics over time, you want to do all the things that you're learning in this course. And the TweetIt platform is really, together with the player, they are really sweet to that. And so when you want to build your simulation, my way to go, and I think this is, we can say this is a standard, is the TweetIt. And that's why this is the great part of this course. But then, when we want perhaps to run parameter scans or searches efficiently, when our main interest is gathering simulation output in many simulations, not necessarily looking at the intermediate step of the simulation itself. When we want to run many simulations in parallel in high-performance computing or distributed computing environments, then we need to use the API. And you can imagine a workflow whereby you build your simulation, you create it, you are satisfied with how it works. It looks like that, familiar kind of layout where we can play around with parameters and set some kind of standard. And then we can wrap up our simulation into a vanilla flavor wrapper. And we can create some access so that we can instantiate it in different flavors and try those flavors, perhaps using high performance computing cluster. The angiogenesis simulation we will try is not that heavy. And I hope that if you follow along by Saturday evening, we will be able to run a parameter scan, each of you on your own personal laptop, but not necessarily. I don't guarantee that, but it might happen. I think if we follow along, that should happen. And then what we get data. That is the core of scientific endeavor, right? We need data. And then out of data, we can generate this fancy plot. As I said at the beginning, we want to modulate our parameters. So each of these dots in my plot represent an individual simulation. And we have different cases. The simulation, as I said before, gives different outputs. And we want to study that. And so we data wrangle, we do other stuff. But to do all of that, we need the API, or at least it's much better to use the API. What's the difference? Honestly, not very much. This is the Tweedit. You are familiar with that now. The file structure of Tweedit. We have a Python script, we have an XML script, and we have another Python script. The steppables, we have seen a few of those. And 3 files. Well, one more that really is a pointer to the tree and organize all of them. Then what all of this turns into a Jupyter notebook? Well, honestly, we can do in one file only. We can put everything in a single file. That's why the API is well designed and it's easy to implement. And you will see that it's really mapping one-to-one all the things that we do in Tweedit and in the XML part especially. Or we can do a full Python script that you can run from a Python environment, wherever. And this is composed of really maybe 1 or 2. You will need some commodity files, but it's really. So you see that from here, I think my take-home message from this slide, we are not complicating the work. We are making it a little difference to enable different opportunities and to catch some potential that we can have with the CompuCell platform as a whole. This is the cheat sheet about installing CC3D and Python package in a code environment. I think TJ will have a whole lecture later on today, so this should be kind of redundant, but it's there for you to use if you want. And it's really usual thing we have seen before. You need to create an environment, you need to activate it. If you want to use Mamba, speed up thing, you want to install CompuCell using these facilities. If everything works, you are able to run either Tweedit or Player from your code environment or do what we are going to do. For doing what we need to do today, you need a little bit more. You need to install in your environment other packages. One of these that is very essential for today is Jupyter Lab. Is equal to Jupyter Notebook, but Jupyter Lab is kind of the newest version, so perhaps we can use that. And then one tricky bit that comes only because of Jupyter, but if we want to follow along with Jupyter, we have to do that. We have to install this IPY kernel that might come with the Jupyter Lab installation, might not. So we can check if it's there. If it's not there, we can install it with Mamba or Conda install Conda Forge IP kernel. Once it's installed, we need to link our new environment that we have created with this name, you see here, to the kernel. And I will show you what it's worth. And you need to say which environment it is and which name you want to see displayed in Jupyter Notebook. And I think that now we got to the point where I want to familiarize very quickly with the Jupyter API, but I think we can do just by sharing the notebook. But before that, I want to show you the actual simulation. So we start from a familiar ground. This simulation is exactly the one that you will see implemented that it runs exactly the same, and it does the usual things: metadata, pods, cell type, volume, center of mass, neighbor tracker, pixel tracker, contact plugin, chemotaxis plugin, diffusion solver that we have just learned today, uniform initializer. That's it. So we don't need this anymore today. And so I will cancel, so I will use my terminal for other endeavors. And the one that I want to do is, if I can, I hope it will work. It should. I can bring my terminal here, and we can do Jupyter Lab. I'm within my environment that I created as for cheat from the cheat sheet. And so I should be able to run this command. This in time should open an interface because, okay, while I'm sharing on Zoom, things are a little bit slower. It's doing things. And I should have Zoom something popping up in my browser. Yes, I have it. And I will share with you if my computer allows me. Yes, we are here. Well, as promised, we have only one file, and it's the same file that is linked in the link that I posted at the beginning of this short session. And you can open it if you have means like the one that I showed in the cheat sheet. There are other means. I think you can open in Colab and in other platforms. Or if you have VS Code, you can open it from there, and it will work as far as you have a proper kernel with Compusel 3D installed. And without further ado, I will just go to the main interface. That is what we want to see. You have seen it at the first day on the Python bootcamps with Aiden. There are very few differences, so just that we are in a short, and I think you want really to take some lunch before a heavy afternoon. We will just keep the basics, but this is the play button whereby you can click play when you're pointing at the cell, and you will have the output of your cell. And the other important thing to notice, we have just linked our environment with the IP kernel. So it's important that we select the kernel. I have already selected because it's not the first time I do this. Normally you will be starting with this. And if you have done everything correctly, you should have this as well. Select, and I have a kernel run. And the other thing here, these are just markup cells with just fancy format text, and do another thing, give us an index that we can follow for these things we are doing now. And please, James, wave me a hand when I need to go fast because I don't have a timer with me, but it won't be long, I think. So important things about instantiation and simulation Python only is that we have to do some import first. We have to do import the so-called CD3D sim service, which is needed to instantiate simulations. We need to import our plugins as from the PyCore spec module, and these are familiar names you will learn that you are learning to recognize. Then we want some standard library, NumPy. We want time to track execution time. We want OS to be able to work with system folder files. And we want widget to make for today an interactive session where we can do things. Then let's say that I won't run this code because I will run all together at the end so we don't get confused. The steps then are pretty simple and are very, very parallel to what you do in XML when you build a Python script. The only thing that is less clear what you have to put inside things, and so some facility comes at your help. So first of all, we want to instantiate some variables, and we want to instantiate some other variables that point to our directory. So working directory, we can use the OS library that get access to the current working directory, and we can plug it in with output. So we set the variable output here as an output string that we can use later on. And then we start with the usual stuff. We have pods core, which will have in itself the pod specification that we have in our pod section in the XML. And here, I put it in the notebook just as an instruction, but I will just showcase that here. If you need help, let's say that you don't have this. We're just starting, we don't have this. And how do I know what to put in pod score? Now I will put it back before it cancels. But if within Jupyter Notebook, there are facilities like this that is show contextual help. And now, in the case I've done my imports, and at this point I have really to run the import cell. When the import cell is run, and I guess should be all done. I don't know if it's done. Let's go. What's called? Okay. Yeah, perfect. When the black dot is here, it means that it's running. Now that I had done my import, now the system knows what pod score is that I imported before. And if I click on it with this contextual help on, I can read the initial signature, which tells me exactly what pod score wants to have and all the variables that we need to put inside. So this is useful to know for the times you don't know what to put in, and if you want to relate to the. You can always use the XML as a guide, but sometimes you don't know the exact name that is being used there. Or you might even try this kind of line. I won't run it today, but if you do this on a module that is being ported, you get all sorts of information available. Then we want just to move up fast. We want to specify our metadata. We want to specify the cell type plugins. And we do this like before. We create an object sim meta. We instantiate an object metadata that is an object of the Python library that we imported here. Just for a reminder, you see PyCore specs, import pod score, metadata, and all of this. And the other thing that we need to do, since we have created a list of our specification, each time we create a new specification, we append it to our list. And at the end of what we do, we will just import everything. Then we move forward with cell type plugins, volume plugins. We just register center of mass, neighbor tracker, and pixel tracker, which don't need parameter for our simulation. Contact plugin specs. These are the way you do that. It's a little bit more involved than the previous one. You instantiate the contact plugin with a neighbor order at 4, for example, and then you add parameter with a method of the contact plugin object that we are where we are using the sim contact commodity variable to store it, and so we can do sim contact parameter new medium EC. Sometimes I'm not sure that it will happen now. Contextual help will give us stuff for the contact plugin. Definitely should do that. Yes, it's doing, and it tells us what it can give. Sometimes it gives us info about parameter new as well. If it doesn't, in the same exact contextual help of contact plugin, you go down until you find your function, parameter new. That might be down there somewhere. And you will, anyway, I don't find append. Remove, it will be out. So anyway, it will be here somewhere, and you will find what it wants to have in its specification method, okay? For now, it's written here, cell type 1, this is the kind of thing he wants, cell type 1, cell type 2, and the energy contact between the two. Then we want to go to the diffusion solver specs. As you have seen today in previous lecture, these are a little bit more involved than other plugins. You need to define a few bits. So it's important that it's a little bit more complex also, the Pythonization of the thing. But it starts like all of these things. You start making an instance of your diffusion solver FE, the same exactly that we use today, and then you create a field. While you create a field with the field new method of the diffusion solver FE class, and you give a commodity variable its name, we call it VGF because this is what we want. And then we set all the parameters for the VGF things, the boundary condition, which we want to be periodic for this simulation, the diffusion global constant that we want to be 1, diffusion global decay, and decay by type that in this case is 0. It's just here for example. Then we have to set secretion parameters, and in this case are cells secreting. So we want TC to secrete this amount. And then we want to append everything to our usual list of specs. So a little bit more involved, but not that much. Once you are familiar with XML, I think everything comes familiar after a couple of times you do that. Chemotaxis, Pedro will explain that tomorrow in detail. So I won't go very much through this, but you have, again, a slightly more involved way of defining the parameters needed to be put into the chemotaxis plugin. And so in this case, you instantiate it later on because you build the parameter cases before, and I won't go through this for the sake of time. But you see that the numbers I'm putting in are always the same, are always those that you would put in the XML. So there is a one-to-one mapping to what you put here and there. And then we have an uniform initializer that we have used throughout the day, and you put exactly the same thing that you would put in the initializing in XML. And then you will append all of this to each one of the things you have created to your specs list. And then finally, we are ready to initialize and run the simulation. To do that, we need to take, again, a commodity variable and use it to assign the sim service class. We give an output here. We can give very many other things to this, but it will be for later. And we register of the specs defined above. We take our specs list that we have filled until now in all the cells before, and we register into our AngioSims, which is, again, an instance of this class. Then out of our AngioSims, we can run it, we can init, and we can start. And this will run the run method, the init method, and the start method in all of your simulation and in the steppables if you have that. I will go quick over this. One, because I'm not the best expert on callbacks in Python. And two, because it's slightly involved and we are like slightly short of time. But to set up sliders in Python, essentially use the mechanism of callbacks, which are functions that check whether a certain event in your simulation is happening, or in your Python script is happening, and relays it to certain function. And then there are facility in our API to simply relate to the Python, to the CompuCell simulation, please change this value for me because the slider has changed. So I won't say more than this for that. And so you can probably asking TJ is the best also to have more detailed information for this. But this is the code that you need to implement a couple of sliders. And then we can run the simulation interactively. This is where I wanted to go for today. We can instantiate some visualize object, which will be windows. One of those, I want to be my VHF field. And I do something to essentially visualize that. And I need some of the library imported to instantiate a run button. And this is what I will do. So one funny thing about Jupyter notebooks that have been organized as I shown here is that you can just select my heading and run all the cells for the heading. And now, if we are lucky, we will have a running simulation. It will be slow, I can tell you. First, because Zoom is running, and second, because I'm not advocating necessarily for you to use this to run interactive simulation. Tweedit is much faster, much more streamlined. This is just for demoing and to show you that you can do this in Python only as well. It's useful in certain instances, but not necessarily. So you can now slide my parameters. Let me make something very obvious that will change because it's not very reactive at the moment. And let's do like this. I should see my field filling. Things should change. Okay, you see my things changing. I have a little chemotaxis, so the cells do essentially little sprouting. If I change it in the decay, very little decay, very long taxes. Perhaps the things will go completely the way around, but it's not fast enough, the update to show you the update right now. But this is what I had for you in terms of how easy, after all, is to implement a simulation after you know clearly your XML code and to translate it into Python. And since this is not very much updating, I will just stop running it. And I guess perhaps it's a little bit too late today to go through this. It's just to say, you don't really want to do all of this in Jupyter necessarily. Jupyter is a way to show you today for education purpose what we can do. It is a nice environment to play things one at a time. But then if we do the things that we want to do, parameter search and so on, we want really to have an independent Python script doing all the things. And this might look like exactly like this. The import will be very much the same, but perhaps we will define a class. Cholangiosyns is initialized with all the things we have seen today, very quickly. Same thing exactly, but just in a class. So it will be a little bit more. You have to move things around. And then perhaps we will instantiate in our class a run methods that does the thing that the run method does. And we might, if we run this, we can implement a new steppable. And once we have this, we should be able to run the simulation and print the results. Just for demo purpose, it might actually not work for some imports or something, but if it runs, it will give you an idea what's happening, what's going on. Let's see if it happens. And anyway, or let's see, give it 1 minute just to show if something happens. You see that it's getting idle quite a lot. In the meantime, I will just put this forward so that you can, okay, this is us again, but just you can start filling the poll, and feel free to provide comments and let us know how things are going with this course. And with any question that you might have, I can happy to take them now, later on, and we'll have more of this on Saturday. So don't feel urged to stay now, and please go for lunch if you want. So this is taking a little bit of time. So in the meantime, I'm happy really to answer questions, and it pops up and manage to sort out the running while we talk. And I guess that's it for me. So I'm happy really to take any question and things. That was a good reminder. Fill the poll, please.
I have one question is, can we use the Python scripts that you shared with us to analyze the data, the output that we have run in the local CC3D software in our PC?
This is something, it looks like in a browser. I zip very quick, but this is happening locally on your computer. And that's demonstrated by the fact that it's taking a long time because I'm running Zoom and I'm running things. And so, so this is happening, despite it is in a browser, Jupyter is a browser interface for stuff happening on your computer. So it's happening there locally. And if that was the question.
No, actually, I want to use your script to analyze the output of the CC3D local software that we use to run our simulation in our local computer. If we can use your code to analyze the output of it.
I've shown you a little bit of if the outputs that you mean are the numerical one that are not popped out yet, but there are numerical output of the simulation that comes out of the steppable that I will show you on Saturday. And this output matrix, so and it runs within the code. So you can output either in the by TweetIt, if you run this simulation and you finish it with this code, and with that particular steppable, it should run and give you the same matrix. So
Okay.
in other words, or by taking another angle, this code is exactly what you have in your TweetIt in one sense. And so is exactly doing the same thing. You're just focusing, probably, I've skipped through the interactive simulation because I don't believe that is the easiest or the most important part to stress on this particular way of writing CC3D simulation. But here you normally focus again on numerical results. And I'm very sorry that for some reason it didn't work out right now. Let's do this again if it happens. I hope I answered your question. Otherwise, please feel free to get in touch and we can discuss this later. No problems at all.
Okay, great. Thank you.
Oh, it's happening. You see, he's running everything headless. We don't see the usual nice plots because this is not the scope of this simulation. Actually, I set the visualization as false. Is running slow. Normally it goes at 56 tops iteration per second without zoom, but then it in a minute probably will give us an output. And after this is there, I'm really done for today. So I hope it was useful, and please get in touch if you. But more than with me, perhaps TJ is the best person when you want to learn this. The way of doing this, but I'm also available for any question, anything you might want to know.
Yeah, I do molecular simulations. So in general, I just run the simulation and then we analyze the trajectory. So that is why I'm wondering if we can use any code to analyze the result. So we can get some figure based on the data we generated.
Yeah. You can generate either screenshot in headless mode, but you can save a screenshot as files, and then you can generate data. And the typical use will be run everything in a cluster, run 20,000 simulation for me, and then give me back my snapshot in this folder and give me back my data in whatever format. It might be a CSV or something that is convenient for that data stream, and then you can analyze using your usual way. So essentially, this is what I've showed today is the way of taking Compusel 3D, wrapping it in a box and using it as a gray box simulation where you have input and output. And that goes in Python, and you can use any Python script to run that after you have wrapped it up correctly.
Okay, cool. Thank you.
Welcome. Now we are really 95, 96, 97. Really close to the end. And finally, we have some performance report. My kernel crashed. And these are the data that I want to show you. These are the parameters that we have used for this particular one. And these are the output of our simulation. Number of regions are those that I've plotted at the beginning. And that is all, folks, really for today. And I kept you out of lunch for much too long, I think.